Hello everyone, my name's Logan. Welcome back to the lecture hall. Today we're covering section 4.1, maximum and minimum values of our UCI Math 2A single variable calculus course. So let's start with a definition. Let C be a number in the domain of f. Then f of C is the absolute maximum of f if f of C is greater than or equal to f of x for all x in D, which is our domain. And you say, oh, look at this little triangle symbol. It's like a V, it's like an upside down A, I guess. Well, what does that mean? That means for all. It's just math notation. I'm going to write that out because I don't like writing the words for all because it takes longer. So just know every time you see this, that means for all. So when it says for all x in the domain, that means that every single x, when you have f of x, f of c is greater than it, and that is the absolute maximum. Let c be a number in the domain of f, then f of c is the absolute minimum value on f if f of c is less than or equal to f of x for all x in D. And it's the same thing here. It means that f of c is the smallest number, right? So it's like the smallest output of the graph. Or smallest output of the function. Alright, we got two more definitions, local maxes and mins. The number f of c is a local max value of f if f of c is greater than or equal to f of x when x is near c. And it's not saying all x in the domain, it's just saying when it's near. And so the number f of c is a local min value of f if f of c is less than or equal to f of x when x is near c. So now you're like, okay, what do you mean by near c? Like, I don't get it, blah, 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 whatever. Well, let's draw a picture to help illustrate these four definitions. So, let's say we have a curve that goes from here to there, all the way up and down. And it stops here. And it's just the interval from here to here. Well, what is going to be our smallest point? It's going to be right here, because this is the smallest y value, our smallest output. And then, so that's our absolute minimum, right here, because it's, farthest down on the y curve. And then we have our absolute maximum up here, right? And we see, okay, well, that's up here, that's the absolute max. But we still have these little humps, right? We have this little hump here, and we have this little hump here, where it goes up, and then it's the max, and then it goes down, and then that's the smallest, and then it goes up again. These are what we call our local max and our local mins, right here. So this is what it is. This, local min, or absolute min, local max, local min, absolute max. So that's a good way to visualize what we have. Now on to the extreme value theorem. It states, if f is continuous on a closed interval, AB, with the closed bracket symbols, then f obtains an absolute min, f of c, and an absolute max, f of d, value at some numbers c and d in AB, in the interval AB. And so what's very important is f has to be continuous and a closed interval, right? Because if you were to just say from, I don't know, negative infinity to positive infinity, you could have something like x cubed that goes all the way up to infinity and all the way down to negative infinity, and it won't have a max and min value because it goes, to infinity and negative infinity. But that will not be a closed interval, right? Because if your domain is all real numbers, it's not closed because negative infinity, positive infinity, they're open brackets. They're more, infinity is more of a concept than an actual number. But if you stopped it from, I don't know, let's just say that's negative 3 to positive 3, then it's a closed interval and it's continuous, right? So then your max will be here and your min will be there. So this is the extreme value theorem. It's extremely important. See what I did there? That was stupid, sorry. But memorize continuous and closed interval. Now, onto Fermat's theorem. I'm not sure that's how you say it, but it states if f has a local max or min at C and f prime of C exists, then f prime of C equals 0. So what is this saying? It's saying that if there is a local max or min on your function, the derivative at that point C is equal to 0. But you can't just set f prime of C equals to 0 and just solve for it, because sometimes you won't get what you're looking for. Sometimes you may get a what's it called? A point that does not exist or something like that. Next, the definition, critical values. A critical number of a function f is a number C in the domain of f such that f prime of C equals 0, or if f prime of C does not exist. So what's a critical value? It's just a input, your C, such that you get, when you take the derivative of it, you either get that it does not exist, or it is equal to 0. And if it is equal to 0, then it will be a local max or a local min from Fermat's theorem. And then this states, if f has a local max or min at C, then C is a critical number of f. It's a critical value of f, right? So you can kind of use these with each other. Now on to the last part of the lecture section. This is the closed interval method to find the absolute max and min of a continuous function on a closed interval. Okay, first, find the values of f at the critical values of f in AB. So what is that? You basically find the derivative of f, set it equal to 0 to find your critical values, but make sure you don't get something that maybe does not exist or whatever it may be. 2. Find the values of f at the endpoints of the interval. So what are the endpoints? You find f of a and f of b. 3. Now you compare all of them. You compare the values that you found from the critical values, and then you compare f of a and f of b to all the other values that you found, and the largest one will be the absolute maximum of the function, and the smallest value of steps 1 and 2 is going to be the absolute minimum. So it's quite a quick process. You take the derivative, find the critical values, you then plug in the critical values, and then you plug in the endpoints, compare all of them. The biggest one is your max, smallest one's your min. So that's it for the lecture portion of the video. Let's transition into the practice problems. Alright, we're doing number 7 and 29. What do they say? This says sketch the graph from 1 to 5, and it's a closed interval, right? And this is going to be a continuous graph. So what does it say? It says absolute max at 5, absolute min at 2, local max at 3, and local minimum at 4. Okay, well, let's start with our graph. We just draw it out, and then we're going to go 1, let's say that's 1, that's 2, that's 3, that's 4, that's 5. And we can kind of draw it any way. All we need to know is that our absolute max is at 5, our absolute min is at 2, right? Because that's 1, 2, 3, 4, 5. And then it states a local max at 3, and then a local min at 4. So all it has to be is something that, and then it just you just follow the curve. And I'm just kind of placing these, right? I guess the one at 5 should be more up here, right? So how did I do this? Well, I just kind of placed them wherever I wanted, because I just know that the smallest one has to be at 2. So I just put it below the x-axis. It doesn't have to be. It could be like right here even. But I just put, okay, this is going to be my lowest one. And then I know 5 is going to be my highest one, right? It's going to be the max. So that's going to be in between. And then I know my local max is going to be higher than my local min, so I know 3 has to be higher than 4, but 3 still has to be less than 5, and then 4 has to be greater than what's at 2. So it just kind of looks like this. Now on to number 25. We're doing 29. Find the critical values of f of x is equal to 4 plus 1/3 x minus 1/2 x squared. How do we do this? Well, we need to take the derivative, set it equal to 0. Okay, so f of x. What's f prime of x? Well, we get is equal to, well, derivative of 4 is 0, plus 1/3 x is just 1/3, power rule, minus power rule of 1/2 x squared is 2 comes in front, so then we just get x. Oh, that's not too bad, because 2 comes in front, right, cancels out with that, boom, and then minus 1, we just get x. So what are we left with? We get f prime of x is equal to 1/3 minus x. Then, how do we get our critical values? We set it equal to 0. And we do 0 is equal to 1/3 minus x. Okay? And then now we just solve for x. We add x to both sides, add x to both sides. And we get x is equal to 1/3. So then we get that our critical values are, okay, what do we do next? Can anybody pause the video, see if you can do it, and then play it, and then see if you got it right? I don't know. What do you do next? Well, you have to plug it back in, because our critical values are, well, so here we have our critical value. But if we want to say find the critical point, that is our coordinate pair. It says critical values, but we're going to go on further. It said find our critical point. Well, what do we do next? We take this 1/3 and now we plug it into the original function. And what do we get? We get that this is equal, we get f of 1/3 is equal to 4 plus 1/3 times 1/3 minus 1/2 times 1/3 squared. Okay, what is that? That's equal to 4 plus 1/9 minus 1/18. Right, where do I get that? 1/3 squared is 1/9 times 1/2 is 1/18. And then what do we go? We keep going. 4 plus, well, how do we combine these? 1/9 minus 1/18 is just going to be 1/18. And then we get it's just equal to 4 and 1/18, or something like that. And then we want to say, oh, our critical point. Well, it's a coordinate pair, so it's going to be 1/3, 4 and 1/18. And that's going to be our critical point. So, that is all for the lecture or the video today. My name was Logan. Thanks for watching. Have a great day.